It looks kind of dark. Is there a reason for that?
I think it's because I got it tilted. Yeah, yeah. There you go. Let's begin. I said begin. I said begin. I would not say let's dig in. It's not a barbecue or something. Come on.
Lock the door. Yeah, it's the first one. Yeah, I got figured in. Because you just No, yeah, you're right. I did. Somebody recorded. I did the same night, but I just don't want to lift it. Right? It's just like, oh, because that was in the first. Okay, so something why. That's in the first. You. Just the first two. I just started. I figured it out. I just.
No. This is way longer.
I don't think so. I think you can only just do it. I'm not saying that it's like yeah. Someone in here. I recorded you in class.
We get a moment where he's like off camera, like walks off the screen.
Yeah, I don't think I think that's more. I didn't have a really lot of things yet.
Like my head.
Oh wow.
Tell me about it.
What did you get? Did you go to the bathroom? Like wrong. You're right.
Yeah.
After all the snarky comments you make, we still got to use the bathroom. Sounds like you're early this year.
Sure, thank you.
Thank you.
What is that smile for?
You guys are.
I don't know.
All right, I will begin. I will begin with a word of prayer. All right. Dear Heavenly Father, we thank you for this day. I thank you for these students, most of them. Help us to glorify you what we do this day and to learn a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. You know who you are. See here. All right, so let us work some problems. Example 1. So there will be a quiz Thursday, all right?
It says it was for today. Shut up! Stop it.
Let's see here. Yep. And on it will be on the material that was covered last week and possibly the material we covered today. With the could be. All right. Some of you are like, oh man, I need to show up for every class this week. Ah, dang it. So, yeah, it's true. Okay, so how should you solve this problem? I will use this whistle if I need to. What, yes? Take the x root of both sides. The x, like raise both sides to the 1 over x. I mean, I guess you could try that. So, yeah, true, but now it's like you replaced one problem with just another, right? I mean, so like you could do it. Sure, yes.
Can you make the bases the same?
Make the bases the same. I like that. So this is actually what? This is 2 to the 2, right? Raised to the x power, which is 2 to the 2x raised to the equal to 2. You can put a 1 here, right? And then by the 1-to-1 property, this tells me that 2x is equal to 1, so x is equal to 1/2. Very good. That is the right way to solve that problem. What if you're stuck with something like this? 4x equals to 7. How do you solve this kind of equation? See? So the first one I started with is from section, that's section 4.2, number 71, all right? And give me a second here, let me look up where we're, so I recommended homework problems to you guys, right? And so which ones are we supposed to be looking at here in principle? So like section 4.3 actually. So we'll excuse me, we'll get over there and do some of those in a second here. But I want to do a few more of these 4.2s. So this is a section 4.2, number 71. This one here I just made up. I don't think you'd find this problem in section 4.2. See, because this one you can't solve the way we just did the other one, right? So the way to solve a problem like this, I mean, there are various ways, but one nice way is just to use the natural log. So if we take the natural log of both sides, natural log of 4 to the x is equal to the natural log of 7. So ln is the so-called natural log. It's actually log base e, where e is that number due to Euler that I introduced last time. All right? Now this is a super nice thing to do because then by the properties of logarithms, right? And maybe I should remind you guys what those are, right? So what are the properties we have to work with? We have, a to the x times a to the y is a to the x plus y, right? A to the x over a to the y is a to the x minus y. A to the s raised to the t power is a to the st, right? These are our laws of exponents. And those are true for what? I'm assuming a is greater than 0, okay? What are the laws of logarithms? If we have, let's say, log of a times b, we get log a plus log b. If we have the log of a over b, we have log a minus log b. And if we have log of a to the power p, we get p times log of a. So those are your logarithm laws. Now I wrote that with log, quote unquote, right? But you can replace log with, like, you could take this log and you could make it a natural log. You could make it log base 3. You could make it, LG if you like. LG is log base 2. That's used in computer science sometimes. Those rules are true for logs of an arbitrary base. All right? So in a problem like example 2, when I don't have a preference, right? Like I've got a 4, I've got a 7. Which one should I, base the problem on? Well, I don't really care for either one of them. So I just use natural log and kind of split the difference. Okay, so what happens? The x pulls out. We get x natural log of 4 is equal to the natural log of 7, and then solve for x. X is equal to the natural log of 7 divided by the natural log of 4. And there you go. That's the answer here. Do you guys, any of you remember another way to solve this problem? How about graphically? You could solve it graphically, right? How would you solve this graphically? You say, well, with a graph? Yeah, that's true. So y equals 4 to the x looks something like this. Y equals 7 looks something like this. The place where those two graphs intersect is the solution. That's where both equations are true. So there you go. That's that point of intersection right there. Where is it? Well, this point right here is something like 1, 4. This point right here, my graph's not very much to scale, is it? So this would be 0, 1. This up here is, natural log of 7 divided by the natural log of 4, 7. That's that point of intersection. Now, do you think graphically is a good way to solve these? Not really, right? What's another way you could solve example 2? Another way you could solve example 2, instead of using natural log, maybe we could use, log base 4. If we take the log base 4 of the equation, what happens? How's that work? So you've got log base 4 of 4 to the x, right? Equals log base 4 of 7. Yeah, and this exactly the left-hand side is literally just x, and the right-hand side is the answer. Now, at this point, you might be like, wait a minute, what? That looks different. It does, right? So to maximize your complaining on the course evaluations, I will work this problem yet another way. So when you're making your course evaluations and airing your grievances, you should cite this exact example. You should say, he did one example 5 different ways. I just needed to know one. How dare he, right? Something like that. I show you guys different ways because I think it's important to understand the problem more than one way. So and sometimes looking at the problem from different ways gives you deeper understanding into each of the ways. Admittedly, if you're completely lost, that never quite happens, right? But anyway, so another thing we could do is we could take log base 7 of the equation, right? What happens if we take log base 7 of this equation? Well, this time, we don't just get x, right? Over here, we get x times log base 7 of 4 by the property of the logarithm. We pull the power out. What's log base 7 of 7? That's equal to 1. So the answer is 1 over log base 7 of 4. So you mean to tell me that this solution, that solution, and that solution, they're all the same number? Indeed, they are. So there are interrelations of logs of different bases, which can make answers look really different if you choose a different base. And so one of the things that you should know about is the change of base formula. What's the change of base formula? Here goes. If we have log base b of x that's equal to log base a of x divided by log base a of b. This is how you can convert from one base to another. So for example, I'll finally get us to example 3, but it's still going to be about example 2 actually. We can see this in practice, right? So like if I look at what did I have? X is equal to what was it? Log base 4 of 7, right? Maybe let me not use an x in this thing. Let me replace this x with anything else, like, oh, I don't know, Pac-Man. There we go. So in this case, the Pac-Man is 7. All right. My original base is what? 4. And let's think about. This would be equal to log base e of 7 divided by log base e of 4. But remember, log base e is another way of saying the natural log. So that's actually natural log of 7 divided by natural log of 4. So you see the answer that I gave in my first run through example 2 and my third run through example 2, they're actually the same answer by the change of base formula. All right?
So
that one's weirder, but yeah.
is there a reason why we can put e there? Is that just because of this equation, or?
Oh, you can change to any base that you want. For example, if I change this instead to base 7, let's see what happens. If I put a equals to 7 instead of, e, I would have log base 7 of 7 divided by log base 7 of 4. So apply change of base formula, putting my new base as 7 rather than e. What's this get?
1 over log.
Yeah, 1 over log base 7 of 4, which by the way is what? Our other answer for the problem. They're all the same answer.
So you can just put a over as
Yeah, I mean, you could, indeed, we could solve this equation with any base that you like. So I usually just use natural. Why do I use natural log? You're like, the e is not even in the problem. Why are you using that? There's a simple reason. It's because your calculator has a natural log on it. It's a big button. You don't have to do anything special to use it. It's right there. So like natural log is a standard sort of choice that's made. A lot of log. There's usually a log base 10. That's called the common log. Like there's a log base 10 on your calculator too, probably. In fact, mine, I have a log and a natural log button. So you could also do log base 10. Let me do another exam. What does it have to do with trees? All the logs. So horrible. So that is the appropriate age level. Yes. Let's see here. So that's what you're going for. I'll allow it. How about 10 to the x squared? All right, guys. Okay. This is not what I like. You should be afraid of the whistle. You shouldn't be embracing the whistle. I need to have like a play achy break, like a button where if I press the button it plays like the achy breaky heart or something more. Do you guys know about the achy breaky heart? You don't know about it. It's before your time, right? It's a horrible thing that happened. It was the harbinger of Miley Cyrus's to come, you know? So, indeed. So this equals to, let's say, 100x. Can we solve that? So here, so you guys were just asking me about common log. I think this is a good problem to use the common log, the log base 10. So if I take log base 10 of both sides, how's that go? Now one of you one of you told me to change the base on the original problem. That was good advice. You could do that here too, right? You could rewrite 100 as 10 squared. But or I can just take the log of both sides and then I don't have to think so much. Now log base 10 of something is the something. So this is just x squared. And over here you have x times the log of 100. What is the log of 100? So that's x times the log of 10 squared, right? So generically speaking, let me write down some identities for you guys. The natural log of e to the x is x. Log base 10, which is just log, of 10 to the x is x. Log base a of a to the x is x. So these are, different choices we have. I'm using log base 10 right now. Okay, so like log without anything is log base 10. So what is this? This is precisely 2, right? So what are we trying to solve? We're trying to solve x squared equals to 2x. How do you solve that? We divide by x, right? That gives me x equals to 2, and there you go. That's the answer, right? Does this feel wrong? It should feel wrong to you. I've never did this before. Why don't I do that? Yeah? Well, it could. Yeah, we might worry about it being extraneous, but I don't think that's going to be an issue here. Could be plus or minus. No, I didn't take a square root. I just divided by x. Yeah. What's the harm in that? What's the other way we solve? How did I solve this kind of problem before? What did I do? Remember, I did. Like you probably completed the square. Let's see here. Minus 2x. Actually, there was no need to complete the square on this one, right? A more simple technique works here, right? Factor x out. So what is the solutions? X equals to 0 or x equals to 2. So what did we miss when we divided by x? Yeah, we missed half the solution, right? We lost half our points. Don't give me half your points. I have too many already. I really don't want them. You keep your points. So to keep your points, be careful. If you divide by x, that means you're throwing out 0 as a possibility. But 0 is a solution here. Go back to the original problem. What happens if you plug in 0? 10 to the 0. Is 10 to the 0 equal 100 to the 0? It's true. They're both equal to 1. So 0 works. 0 is a legit solution here. Does 2 work? What's 2 squared?
4.
2 squared is 4, right? So we have 10 to the 4. Is 10 to the 4 equal to 100 to the 2? It is. They're both equal to 10,000. So these are both actually solutions here. All right, let me go back and work a couple more easy examples like example 1, because we haven't done enough of those yet. I've been focusing on the more hard stuff here, and I should go back and do more basic problems. All of the basic problems you can solve with the more sophisticated log techniques, all right? Like all of the problems I'm about to solve, you can solve with logs if you want. So example, where am I on? 5, yeah. So let me just write down, I'm going to write down a bunch of problems here right quick. So 125 to the x equals to 5. Example 6. 32 to the 2x equals to 16 to the x minus 1. Example 7. X to the 3 halves equals to 27. Example 8. Let's see here, another one. Square root of 2, parentheses, to the x plus 4 equal to 4 to the x. And example 9, 1 over 32 equals x to the minus 5. Let's see here. So these are all taken from section 4.2. I don't think I have not listed these in the, oh man, seriously? These are not listed in the recommended homework. That's dumb. All right, well, at least I'm doing them for you. So, yep. I don't know. Like, your grader's kind of ghosting me right now. I mean, I don't know. Like,
our mission was.
Wait, you don't grade them?
Our mission
No.
was graded within like a week.
Yeah, she like graded it and turned it back to me like that. But she's not giving it back to me yet. I think that we have come upon the week in her semester where all of her classes have tests, and I'm assuming it will come back to us soon.
Did you grade the tests?
Hmm?
You grade the tests?
Yeah, I grade tests. Yeah.
That's why there's a dinosaur drawn on mine.
Yeah, that's my dinosaur.
I didn't eat my turtle.
I had, I took a class to learn how to like draw counter doodles on tests. It's like third year in grad school.
Counter noodles?
Yeah, counter noodles. Doodles, counter doodles, excuse me. Counter noodles is something else. I do what I can. Let's see here. So, the theme of every last one of these problems is that you can convert both sides to be the same base and use the one-to-one property. When is that a reasonable approach? It's only a reasonable approach if you have the number sense to see that that's what you need to do. If you don't have that, you can just take the log of both sides and solve these problems. You say, which log? Natural log, log base 2, log base 10? Like, it doesn't matter. As long as you consistently use the same log on both sides and work out the properties, you can solve it. Now this is actually what? 125 is 5 cubed. So this is actually 5 to the 3x equals to 5. So therefore 3x is equal to 1, x is equal to 1/3. That's how you solve that, if you can see that. 125 is 5 cubed. If you don't know 125 is 5 cubed, how do you solve this problem? The other way to solve this problem is I would just take the natural log of both sides. The natural log of 125 to the x is the natural log of 5. Or you could take log base 5 of both sides if you wanted. That would probably be nicer. Yeah? Let me do that. Actually, let me just solve this problem one way. I'm tired of solving every problem 2 ways. You're probably tired of me doing it too. So let me stop. How about this one? So how about we look at them both as powers of 2? They're both powers of 2. 32 is 2 to the what? 2 to the 5. So I have 2 to the 5 raised to the 2x. And over here I've got 2 to the 4 raised to the x minus 1. We use the law of exponents. The law of exponents says we multiply them. Careful to distribute. So we've got 2 to the 10x over here is equal to 2 to the 4x minus 4 over there. One-to-one property says 10x is equal to 4x minus 4, right? So if this was regulated by the government and the makers of the logarithm had done their due diligence to have their lobby force everyone to use logs in all their problems, at this moment this would be an illegal solution. We haven't used the log, right? We haven't done it in the professional way. Nevertheless, it's true. So we got 6x is equal to minus 4 X is equal to minus 4 over 6. Answer, X is equal to minus 2/3. See, Xavier, I reduced it. Eh? Okay, it's better, yeah. Ironically, grading is the one place where like reducing is not helpful because the idea is it's like 3 out of 6 points, right? If I write 1 out of 2, then it's like 1 out of 2 points. So like the fraction, when we write fractions in grading, it's reducing it is not a good practice. It's a funny thing. Let me not digress into that. So does this make sense? Now, I would argue here, for most people, this is probably not the right way to solve this problem. I think the right way to solve this problem for most people is just to take the natural log of both sides and let the natural log do the heavy lifting for you. Right? How about this one? How should I solve this? Square both sides. I take your square and I cube root it. So what I do for this problem is I just take both sides and I raise them to the 2/3 power. Yeah. The 2/3 power, that was supposed to be a 3. Good grief. 3, all right, 3. So these cancel to give me 1, and I get x is equal to the 2/3 root of 27. Now that could also be written as the cube root of 27 squared, right? Do you guys understand that? Maybe, maybe not. Let me write the 2/3 in a different way. This we could look at as 27 to the 1/3 squared, which is literally what I wrote here. I just point that out because the cube root of 27 is 3. 3 squared is 9. So I can see x is equal to 9. I didn't even have to pick up my calculator. Of course, you should also be willing and ready and able to pick up a calculator and work that out just the same, right? But in principle, you shouldn't need a calculator for that one. How about the next one?
Could you do the same thing? With the
So I could rewrite 4 as the square root of 2 to what power? How can I write 4 as the square root of 2 to a power? Let us agree that's a weird question, right? That's a weird question. So I think this is a good opportunity for us to use the natural log method instead. Let's do that. Take the natural log of both sides. How's that go? Bless you. Natural log of root 2 to the x plus 4 power. Natural log of 4 to the x. So what it gives us is, it gives us x plus 4 times the natural log of the square root of 2 equals to x times the natural log of 4. At which point I regret writing example 9 right there because I'm going to run out of space. I think that's what I got. I think I got to go high. That's where the success. Oh, almost. So what this gives us is x times the natural log of the square root of 2 minus the natural log of 4 is equal to 4 times the natural log of the square root of 2. Now, did I do that right? I think I did that wrong. I'm missing a sign. I'm missing a minus sign somewhere in that equation. Tell me, guys, where is my minus supposed to be? Am I missing it? So I'm trying to group everything with x to one side and everything without x to the other side. So this times that gave me this term, right? Right, so this should be a minus here because I took that to the other side. All right, so then you can solve for x. So what do we got? X equals 2 minus 4 natural log of the square root of 2 divided by the natural log of the square root of 2 minus the natural log of 4. That's a kind of ugly way to write the answer, but there you go. Now we could combine the natural log of the square root of 2 downstairs with the natural log of 4 by the like fraction property for logs. But I think I'm just going to leave it like that. Yeah.
I am confused by some of the steps that you took to get from the like from the x plus 4. So did you like that?
Let's see here. So this would be equal to x times the natural log of the square root of 2 plus 4 times the natural log of the square root of 2, just distributing, right? And then look at this, what I've underlined in green here compared to that, right? So what I'm doing is I'm moving all of the things with x over here.
Oh,
And then I'm factoring x out once I've done that. And I'm moving that to the other side. And I'm sorry, I would have written more steps out, but as you can see, I planned poorly. I put example 9 here. You're like, you should have just erased it and made yourself room. Well, they'll tell that to me 3 minutes ago, you know? So, what's that? It's on you? I accept it. All right. Let's see. So, this is 2 to the what? Yeah, that's 1 over 2 to the 5th, right? And that's 1 over x to the 5th, isn't it? So this... Exactly. So this is x to the 5th equals to 2 to the 5th. Which indeed, if we take the 5th root of both sides, we get x equals to 2. Yeah. There is something unpleasant to think about there, which is that all you get? You know? Why isn't there more? How many solutions could there be from x to the 5th equals to 32? Let's see here. I'm trying to find a spot to write it here. So think about this. X to the 5th equals to 32. How many solutions could you have from such an equation? Though the question becomes, what kind of solutions are we talking about? Real solutions or complex solutions, right? If we were talking about complex solutions, the answer is there's 5. There's 5 solutions to that problem. Because there's something called the fundamental theorem of algebra, which says that if you have an nth order polynomial equation, you get n solutions, possibly repeated in the complex sense. So it just so happens, though, that x equals to 2 is the only real solution to that problem. So x to the 5th equals to 32. Basically, you get x is equal to 32 to the 1/5 power, right? There are actually 5 complex numbers that you can raise to the 5th power and get 32 from. And if you'll allow me to misbehave for just a second here, one of them is 2. But there's also like a number here, and a number here, and a number there, and a number there, if I remember right. So basically you're talking about like, I can't draw it. Rats. Well, if I could draw a pentagon, we'd be in business. The other 2 solutions, though, the other 4 solutions, they're all complex. So we don't care about those. So long story short, if you have x to an odd power equal to a number, you can just take the root and you get the only real solution, and that's the one we care about. Another example of this would be like x cubed equals to, 1. What's the solution? So you guys are like, well, take the cube root of both sides, right? And that's fine, you can do that. What's the cube root of 1? 1. What happens if I try to factor this, though? I get x cubed minus 1, which is x minus 1 times what? Times x squared plus x plus 1. This is the special form trinomial. We actually talked about this earlier in the semester. The thing is, the quadratic that I factored off, right? This right here is prime, and so the other two solutions that there are to x cubed equal to 1, they're both complex, and so we don't care about them in here. All right. But if you were to picture them, they're pretty neat. They're like symmetrically arranged around the origin in the complex plane. But anyway, let me save those comments for another class. Let's see here. So let me move on. Any questions before I go on? Let me try to find some different problems for us to chew on here. 40. Let's say, try section 4.3.
Mr. Flip, I have a question.
Go for it.
Are we going to have to like expand or collapse any equations into things?
Oh,
Because I saw that in the mission.
Yeah, probably not that. We haven't done that yet,
Okay.
but maybe if I do it now. But I think we have enough on the quiz with finding the formula for the inverse function and solving like these kind of problems. That should suffice for us. We'll worry about the logarithmic equations and the log simplifications on like the next quiz. Yeah, that is a very good question. My eraser shirt. There it is. All right, let's try to work. Let's work some basic. Oops, I shouldn't have erased those. Basic log problems. See if I can find some that are good. So 4.3, I've pretty much assigned every problem in 4.3 if you look at the course planner. So anything I do is relevant. Okay, so here's one. You're supposed to rewrite the equation in logarithmic form. Rewrite in log form. Let's do one of those. So here we go. 3 to the 4 equals to 81. How do you express that in terms of logarithms? What example am I on? 10? Yeah. So this is like section 4.3, number 11. What'd you say?
Log base
Uh-huh. 3?
3.
Okay.
1 4.
Yeah, so, I mean, if you want to find the log form, one thing you could do that's very lazy is you could just take the log base 3 of both sides of the equation, and we get 4 is equal to log base 3 of 81. There you go. That's this exponential equation is interchangeable with that logarithmic equation. So any exponential equation has a corresponding log form and vice versa. All right? I don't find these kind of problems to be particularly interesting. Let's go on to the ones I think are more fun. Solve these equations. Let's look at, ooh, what to even do with this? This one, I'll get stuck on this one some days, guys. Here we have log base x, of 1 over 32 equals to 5. How do you, what do you even do to that? And then the next one I'll look at is x is equal to 3 log base 3 of 8. Oh, that's kind of embarrassingly easy, the next one. So it says to solve the equation. What it's really asking you to do is, that's number 25 in section 4.3. That question really, are we solving it? I don't know. Really, he really is just asking you to simplify. Okay, so going back to this one, what do you do? What to do with that? So what I would do is I would exponentiate both sides, right? Basically just raise this to the, x to that is equal to x to that. So what's x to the log x? They cancel, right? And you're just left with 1 over 32 is equal to x to the power 5. And then we can just take the fifth root of both sides of the equation. So, oh, you said what that? I'm sorry, what was that?
Oh, I was just going to say x is equal to -2.
Oh, 2 to the minus 5?
Yeah.
Or, oh yeah, okay, I got you. 1/2. 1/2 to the minus 5? 1/2 to the 5, right? And so x is equal to 1/2, right? If you didn't see that, though, you could write x is equal to the fifth root of 1 over 32, right? And if you look on your calculator, you should figure out how you can calculate the fifth root of 1 over 32. All right? One way to do that, syntactically, is to do this. You've got like a button to the power kind of thing. Like this is something on your calculator, box to the box, right? So in this one, you want to put 1 over 32. And what power do you want to raise it to? The 1/5 power, right? So if you do that, you should get 1/2. Let me try it out. So, so I've got like a, let's see, where is that thing gone to? I think I have to put in the 1 over 32 first. And then I look for the x to the box thing. I think I need to put some parentheses in. Otherwise, I'm worried it'll just do it to the division. 1 divided by 5. Yeah, it gives me 1/2. So you need to figure that out for yourself because this is the kind of calculation you're going to need to do on the final, right? So, or the upcoming quiz. You need to figure out how to do that for yourself, right? Yeah, the final's cumulative. That's right.
Theoretically, like, oh, this is going to be like a small percentage of the final.
I mean, yeah. I mean, relatively speaking.
The final's going to have like half of the information, or like part of the information from test 1, part from test 2.
It's just all completing the square. It's just like every problem's completing the square.
I could roll with it.
No, please.
No, the final exam is comprehensive, so it's more a question of how much of the class lecture-wise have we spent on this material. That should give you a picture of the percentage. So I don't know, past test 2, about what, 20% of the semester is this material, so it's probably about 20% of the final, maybe 25, something like that. But to understand what's on the final in this material, I mean, there's two things you can look at, of course. The one is the mission 3, right? The other would be the quit.
So that's a mission for the final? Or that's a mission for just this information?
Yes.
But the final's cumulative, right?
The mission 3 is to help you prepare for the final,
But the final is cumulative.
just like the other two missions. What's that?
So mission 3 is cumulative?
Oh, no, mission 3 is not cumulative.
So
Not.
because you said the final was cumulative, and mission 3 would help you prepare for the final, but mission 3 is not cumulative.
It'll prepare for the near duration of the
Right. So it helps you prepare for only a very small portion of the final. Right?
I think, well, is 25% very small? I don't know. 30% maybe? I don't know. So here, what is log base 3 of 8?
2. Well, 3.
Oh, I'm sorry. What is 3 to the log base 3 of 8?
8.
Yeah, just 8. So this is kind of dumb. Yeah, because 3, so 3, well, generically speaking, a to the log base a of stuff equals to stuff. Here, let's look at another one. How about, let's see here. We'll come back to graphing another day. I'm trying to focus on equation solving at the moment. Although you could have a graph of exponentials or logs on the quiz Thursday, like that would be a reasonable thing. We did talk about the graphs last week. 81, 93, 92. Oh, okay, yeah, let's do some of those expanding, collapsing like you're talking about. Again, I will not put the expand and collapse on the next quiz, but I do think we should start talking about it. Damn, I keep forgetting my eraser shirt. So basically this, what I'm about to do, we're just utilizing these rules of logarithms for simplifying, all right? And so here they go. So this is like section 4.3, numbers 83 through 92. These are some good examples. I'll work one of them. So here we have log base a of x plus log base a of y minus log base a of m. We're supposed to collapse these into a single logarithm. So how do you do that? I can do it in two steps, right? So my step one will be to take the first two and write this as log base a of xy. All right? So I used this property right here, that the log of a sum is, the sum of the logs rather is the log of the product. And then if we have subtraction, that becomes division. So the answer here, log base a of xy over m. Let's see here. So that would be my example 13. Example 14. So this one's kind of like number 19, but I'm going to change it up a little bit. Suppose you have 5 times the natural log of x plus 7 plus the natural log of, 2x plus 9. So this is like number 90 in this section. Again, the instructions are to collapse it into a single logarithm if you can. All right. So what do you guys think I should do? What do we do with that 5? How can we deal with the 5? So we use this property right here, right? Log of, I got something in my eye. Log of a to the power p is p times log a. So I'm going to basically think of p as being 5 and thinking of this x plus 7 as being the quote-unquote a. So this gives me the natural log of x plus 7 to the power 5 is equal to, not equal to, but plus the natural log of 2x plus 9. And then one more move, this is the natural log of x plus 7 to the power 5 times 2x plus 9. There you go. So let's work another here. So the next one, we're supposed to find the equation of the inverse function to each one-to-one function. So I'm going to look at problem 113. Problem 113 from this section. And this might be a good warm-up for the quiz Thursday. Because definitely one of the problems on the quiz is going to be find the formula for the inverse function, all right? So here we're given f of x equals to 5 to the x plus 1, all right? And then the question asks us to find formula for inverse function. All right, this is basically number 113 in section 4.3. What was our algorithm for finding the inverse function here?
Step 1, right for y equals f of x.
Yeah. Yeah, oh, right. Step 1 is right, y equals to f of x. That's right. That was our step 1. So we should do that. So here we go. Y equals to 5 to the x plus 1. That's step number 1. What's step number 2? Solve for x, right? How do you solve this for x? All right, so what we're going to do is we're going to put the 5 to the x on one side, and we're going to put y minus 1 on the other. So now at least we've isolated 5 to the x. How do I solve for x? Log base 5 of both sides. I like that. It's a good idea. So if we take log base 5 of both sides, see here we get log base 5 of 5 to the power x is equal to log base 5 of y minus 1. That gives us x is equal to log base 5 of y minus 1. That is the formula for the inverse function. So f inverse of y is in fact equal to, log base 5 of y minus 1. Or if you like it in terms of x, here it is. F inverse of x is log base 5 of x minus 1. It's an interesting question here to try to graph both, right? So what is the graph? What's the graph of the function and the inverse function look like here? That wasn't asked for in this problem, but I think it's good for us to review that again. Because another problem on your quiz might be, here's a graph the inverse function, right? We did those too last week. Okay, so first of all, what's the graph of 5x plus 1 look like? 5 to the x plus 1, it's the y equals 5 to the x graph translated 1 unit up, right? So y equals 5 to the x just looks like this, basically, right? It's got a y-intercept of 0, 1. It has a horizontal asymptote of 0, right? So you're taking that graph and you're just lifting it up 1 unit. That's the graph of f of x. What's that? Closer every time. Well, maybe by the end of the semester I'll get it.
Are you consider my offer?
Your offer, which was that if you miss it, then you have to buy pizza for the class? Is that it? Is that? But what's in it? What if you miss it? There's got to be some kind of blowback. No, not we all get pizza. You have to buy the pizza.
I'll bring you pizza.
No, I don't. No. It's just not for me. That's not.
If you miss it, I'll bring you a personal pizza from Pizza Hut.
No, I think I'm okay. I'm okay. So this is the graph. Here's y equals f of x, right? Where does the graph? What's the graph of the inverse function look like?